Okay. Welcome back, everyone. Welcome back. Okay. So yesterday, I reminded you that we were going to study everything regular as the calculus one student do, right? Every single section we're supposed to cover every single one of them. We're not going to trim down. It's not a short version. Okay, it's a full version in a short time. However, with that being said, I still try to my best to cut maybe at least one section. At least one section that is I deem not really necessary. It's good, but not really necessary for your Cal 2. This one. Okay. I still talk about this one. Maybe 5 minutes. Tops. Okay. And then I'm gonna moving on. So 4.6 is the one I'm gonna drop. Okay. From our study guide and everything. Okay, so I'm gonna skip this one. But I still want to give you a description. What does it mean? What does it mean by studying Newton method? Okay, but in numerical analysis, this method is the foundation. Okay, the first section you learn, you're gonna study in numerical analysis in cryptocracy. Okay, this one actually have you to solve to decipher or decode or jailbreak. How did they find out your passwords? Blah 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 blah. Okay, they keep asking you to change password after around a year, right? Now every company, being a professor, 3 months. Every 3 months I have to change my password. It's just ridiculous. Every 90 days I got a notification. Your password is about to expire. Please change that. I'm running out of password, and I cannot use the previous one. So every time I do that, I put the old one. I put the new special letter. I put a hyphen. I put an at. I put a number sign. I keep stacking it up. But why do they keep asking me to do that? Because they can trace the password. Okay, and actually this one, the foundation of cryptocurrency, cyber security is the Newton method. Why is that? Technically, you try to rotate, right? Let's say my password is the easiest one, 1, 2, 3, 4. Okay. Oops. Nobody do password is 1, 2, 3, 4, right? I hope nobody do that, right? 1, 2, 3, 4. Okay. Yeah, password is password. That is not a very bad idea of giving a password, right? Or maybe my name. Somehow I do that. Capitalize, one capitalized, right? You put the first word capitalized. You have one number, I put one number, right? That's how we do. Special letter, maybe that. But how do they do that? How do they actually decipher, get your password, steal your password? They keep rotating the alphabet, okay? They find a keyword in there, some keyword, and then based on that keyword, they rotate, okay, so A, B, C over the alphabet. If one of them hit, okay, they skip that, jump to the next one, A, B, C, D, and then rotate to on the number 1 to 9. Actually, the number, only 10 letters in the number, 0 to 9, right? You have unlimited number, but they're just a combination of 0 to 9, right? So just roll to 0 to 9, A to Z, that's all. And a few special character. You don't have a lot of option. You have unlimited combination, but you don't have a lot of option. So rotating between them is really easy. So rotating them, technically, they solve for some kind of function until they hit the letter L, or maybe number 1. So that means they find a solution, moving on to the next one. Then they're going to figure out, okay, what is the best way to come up with that solution numerically? Because all of this, at the end of the day, in your calculator, in your computer, it's just 0 or 1, right? Binary, either 0 or 1. It's even easier to translate. So 0, 0, 1, 0, or 1. This one, find solution. Think of a best way to find solution. Starting with a very basic one, quadratic. How do you find solution of quadratic? How do you find solution of quadratic? Normally, how do you find solution for quadratic?
Could factor the quadratic formula?
Quadratic formula. Another way. Okay, so technically there are at least 3 to 4 ways for quadratic, right? Quadratic factor. Next one, more traditional, more old school. Yeah, quadratic formula, right? You have quad formula to find solution of quadratic formula, right? I still remember. Right, quadratic formula. Cubic. You also have a formula for cubic. It's bigger, much bigger. Okay, but that's it. Cubic and fourth, you have formula. Actually, starting with x to the power 5. That's the degree, technically, how many letters of your alphabet is. Okay, the more letter, the more of your degree. But about 4/5 of higher, you don't have formula. It's really difficult. Okay, there's no formula. You have actually to use computer to estimate your solution. Use the linearization, estimate the solution. You don't actually have a formula to get the final solution. So it's difficult, in other words. All right, then we're gonna estimate. How do we actually estimate that? Estimate the solution, linearization. I'm just gonna show you this page only. How did they actually find the solution? Tell me where in here, where's the solution? Where's the solution? Now visualize it. Where's the solution? Where's the solution? This is your function. Where is the solution? Go ahead, just say.
Where it crosses the x-axis?
Yeah, x-axis is there. Okay, figure that out, okay. But it's right here, this curve, I have the function. I need to know solution. I don't know where it's hit. I don't know where it hit. Okay, then like the linearization. Like linearization, I asked you to estimate this. You guessed right with this, right? Right? That would be 5. So this one around 5 point something. Right? That's the idea. You guess. Just pick a starting point, you guess. Here, okay, I don't know, this is my solution. Okay, this is the solution right here. I don't know, pick one right here. Maybe x1. Okay. What do I pick upon there? Okay, what next? Pick upon. It could be anywhere. Okay, pick an initial. I guess my solution may be x1. Okay, that should be around 5. So this would be 6. Okay, I guess it's 6. I don't know, huh? I know it's 5. Okay, next, use the tension line. Use the tension line, actually. I'm going to draw a tension line. Okay. What do you see from this? The tension line intersect the x-axis right here, right? I guess again, is that my solution? Nope, that's not my solution, right? Try again. This point. Another tension line. There you go. 2 trials. I got a solution. One, pick here, draw a tension line, it cross x-axis. Is that verified? Is that a solution? Plug in, is it give you 0? Solution, nope. Another one, done. Okay, so that is Newton's method. That is the Newton method. He just finds a solution without solving for this. Just guess, use tension line, guess again, okay, and then it's really important where you pick the first guess. That is only the downside of Newton method. You have to pick a sweet one, a good spot. For example, if you pick over here, you don't hit anything. Okay, your function doesn't have anything over there, but around here, okay. Every time I do that, the tension line keep getting closer and closer and closer to this way. hence the solution. That's it. Many other ways. Newton method is the foundation. You have Taylor method, you have Maclaurin method, you have Gaussian method, you have Gaussian elimination, you have row epsilon method, you have a bunch of them. Okay, you have a lot of them. And then eventually, if you're in IT, you're in cryptography, not cryptocurrency, cryptography. It's called decipher. If you're in computer science, you have to know this. Okay, that is the backbone of computer science. Okay, so that's the Newton method. Guess the solution using tangent line until you hit it. Okay, for those of you that come in late, I just give you introduction to 4.6 only. 4.6 will not be on your exam, final exam. Okay, so put that away. 4.7. Okay. 4.7. This should be 5.1. It is really 5.1 is a study of integral. Integral basically is the reverse of derivative. Okay. Reverse of derivative. Instead of saying reverse of derivative, we have a better phrase, antiderivative. Okay. We've been studying derivative, right? Derivative of x is 1, derivative of a constant, 0. Now we're going to reverse engineer. Given something, find the antiderivative. So you go back, okay? So that one here. So we have why do we want to know that? We have been using derivative to find velocity, given a position, right? We throw a ball up after how many seconds? I ask you for the velocity, right? I ask you for the velocity. You given a function of position. After 5 seconds, what is velocity? What is the maximum velocity? What is the minimum velocity? And so on. Then, if we have a backward question, if now we have a car's velocity, we want to know the location after a specific time, or if we know the water. Okay, actually, I don't like this example. First example is enough. If we want if we have the velocity, we want to know the position. We need the antiderivative, right? Position to velocity. That is what we've been studying. That is derivative. Right. Now let's say we have this. What would be my position? Now I have velocity. What would be my position? We use okay, I'm going to capitalize this one. Antiderivative. Okay. There you go. Every car would have cruise control, right? Every car has cruise control, right? And now it's more advanced that they actually measure the distance from this car, from your car, with a sensor to the car in front of you, and adjust the distance, right? Adjust the velocity according to the car in front of you, right? Telling that, right? Everybody know about cruise control, right? How is it? No, exactly. And really fast. It's like 80 miles per hour on a freeway. Sometimes 85, 90 miles per hour. So how does it know exactly to measure that? One miscalculation, or the car in the front have an emergency brake, slam on the brake. Your car automatically slam on the brake too before you even know that. How does it measure that so fast, so quick? Within a split of a second. You are studying that. Okay, the backbone behind that. Okay. Okay, the only car's input at that moment is your velocity. You can see in the odometer right away, 80 miles per hour. But how much distance does it need to stop the car? Yeah. Okay. So, formally writing, use capital F. Okay, capital F, whose antiderivative is lower f. Okay. Which is called, this one right here, is called antiderivative. of f. Okay, the big F is antiderivative of the low f. Big F is the antiderivative of low f. Where? How do you know that is antiderivative? It is antiderivative when you take derivative, this right here, return the original one. Okay. Similar to derivative, we will have formula. Yes, we will have formula. That's basically the same formula that I give you every exam. That handout, that is the formula. You just have to go back and forth between them, right? One example right away. One example right away. One example right away. I have x. I have x. What would be the derivative of this?
1.
It's 1. Right. Correct, correct. Then I have 1. I will ask you later on, we'll ask you this question. What would be the antiderivative of 1? Correct. All right. Now, let's play a little game. Zero. This one tricky. Is it 10? Usually, when you want to find that, you're going to think about, right, okay, whatever you think of, you have to take the derivative right away to see if it give you back to this, right? Okay, so if I go with this pattern, so I put 10 here, I take the derivative of 10 right away. Does it give me 0? So, give you 0, right? Take the derivative of this, give me this. Okay, so that is correct right here. A function that when you take the derivative, give you back the original one, right? The derivative of 10 gives you 0. Correct? But
Can't you just use C then for constant?
there you go. Any number, right? Any number. All of this number, any number, when you take the derivative, give you 0. Therefore, antiderivative of 0, it's just not a single number. It's a family, a set. And the set, you can see, constant. See? Right? Okay. So now, right now, I have x squared. That problems, ax squared. That is ax squared. What would be the antiderivative of x squared? In other words, whatever you find over here, whatever you have over here, you take the derivative, should give you back x squared.
1/3 x cubed.
1/3 x cubed, right? Okay. It's not comfortable to know right away. You have to keep rotating until you have formula, then it will be more streamlined. But for now, we're kind of like guessing. Derivative of this, 1/3, take derivative, times 3, x squared, 3 cancel with 3, give you back x squared. Right, so that's how you find antiderivative. By guessing, for now. So f of the capital F, the antiderivative, okay, actually, f of x equal x squared, then the antiderivative. For now, I'm going to write as much as possible for you guys so you can see. Okay, why is that? Because when you take derivative of that capital F, that means you take the derivative of this, which is 1/3 times q times 3 times x squared equal x squared, which is f of x. It returns exactly the same thing. Okay. Okay, that is, I wouldn't say wrong, but that is incomplete.
You need plus C.
Plus C, if you present it. Okay, erase the word plus C. For those of you that haven't heard that, erase that word. I'm going to explain why plus C. Okay, so that's correct. I just showed that to you. Derivative, please give you that. However, I can think of another one. But let's say I bring up another one, g of x. Okay, that means this one different from that one. But at the same time, how do I make it different? I just add another number, plus maybe 2026 there. Okay, so that you can see the difference. Okay, this one. Take the derivative of this one, please. Try that. Take the derivative of this one. What is g prime? G prime is, you can see that, right? X squared. That also f of x. Derivative of this function give you that function. Prove that this function is antiderivative of this, right? By definition of both. So this is also antiderivative. You just prove that the capital G is also, I use the word also, that means another one, antiderivative of f of x. You can see the picture, right? I can play around with this number unlimited time. Okay, I will end up with unlimited different functions. Every time I have a different constant, I have a different function. In other words, the antiderivative of a function, you don't just have a specific one, you have a whole family of them. Remember the constant one? You have a whole family. And that whole family is called general antiderivative. And instead of writing every constant the human can think of, right? Instead, think of that, f equal 1 over 3 x cubed. And instead of writing 1, 2, 3, 4, 5, instead of writing all of, list them on out. C. C for constant. Okay. A general antiderivative, that general technically is like a family or a set of function. A family of function. How do I know that family? Right here. That C give you unlimited options. Right. Okay. So in other words, the best way to diagram this, okay, put a diagram to this, should be this. If you were asked to take derivative, you only have one direction. Derivative. You only have one direction. It goes straight to this. Nothing else. No other result. One and one only. But if you were asked to take antiderivative of this one, this is one option, right? Antiderivative. This, another option. This, another option. This, another option. This minus pi, right? Still give you x squared. Minus 0, right? Unlimited options. one option. Antiderivative give you unlimited option. How do I phrase on this thing? How do I root on this? Basically another one right there, 0, right? Plus 0. So that is technically a number there. All of them, group them all together. There. Make sense? Okay, make sense? All right. Okay. Visualization. What do I supposed to visualize? I just wrote this note. I'm supposed to visualize this, the function, that function. Okay. Visualize this. Given x squared. Okay. X squared. Visualize both of them. The lower f and the capital F. Okay. So lower f over here, capital F over here. Okay, I'm going to draw the lower f, which is x squared. There, parabola. Capital F, the antiderivative. How do you draw that? Don't really care about 1 over 3. That just compress or construct, right? Just care about x cubed. X cubed, that would be that way. But the plus c. Plus c. Go ahead. Shift it up. How about this? It's still plus c. Remember, plus c is like arbitrary, random. Plus c could be -5, could be negative, could be positive. You could plus a negative number, right? That plus c could be this. Don't strict yourself to plus only. Plus c. That c could be anything, right? I can be this. Plus -1. That's still plus c, right? That's still plus c. Technically, it turned out to be negative. So shift up and down. In other words, and remember, you have a family. In other words, that means you have a limited curve like this. That is plus 0, right? Original. And then if I plus 1, I have like this. 1 over 3 x cubed plus 1. If I have -2, maybe down here. Shift down by 2 units. So 2, 1, and 0. There. All of this. And it's actually true. Each one of this, when you take derivative for each one of this, it only give you this one. It's not going to give you different thing. They have the same derivative. They have the same derivative. And if you go back to the section where we graph the derivative, remember, increasing, this is increasing, right? Increasing, then go to 0, then increasing again, right? Okay. Find the general derivative. Now, think about this. Before I scroll down, spoil on the fun. Guess psi. Something that gives you psi. Negative cosine, right? First thing, because we guess right now, we are allowed to have a bad guess, a wrong guess. Eventually, you're going to come to the correct one. So let's say that we have guessing, right? We guess cosine. We take the derivative right away. Take the derivative right away. That would be negative psi. But we want the positive. So how do we have the negative? How do we have the positive? We just have negative of negative. That would become positive. Right. Okay. Always make some space. Give yourself some space because antiderivative is not alone. Every time you find antiderivative, you must have the plus c. It is a family. Don't think of just one individual, not one individual function. this is a family. Okay, I'm going to use the red one. A family. A family. A family. A function. Okay. General. Okay. So far good? Okay. Then we cannot just play a blind game like that forever, right? At some point we're gonna stop, right? Because it's so harmful. It's just bad for your health if you keep guessing, right? Then we have a formula. Go back and forth. Okay, now try it yourself. You can still have the handout. You can use the handout, but remember the handout, the formula. Every exam I give you the handout. You go back and forth. Okay. That means whatever you write over here, check the derivative, give you this. We just have that one. We just have the first one. That is the negative cosine of x plus c. Each one of them should have the plus c. Oh, missing the x. Okay. Try that. Which one is the easiest one? No, easier. See? Yeah, see? Yeah. Okay. Yeah, I agree. C is also easy. Another one. Yeah. The derivative, the e to the x, the e to the x. Then antiderivative will be the same. Right? So e to the x. Don't forget, plus c. Every time, whatever you write over here, try to check the derivative in your head right away. Does it give you this one? If it gives you this one, then correct. Okay. Try that. It's on the way down here, huh? Oh, I have a few requests. Basically, two about changing the group. Just a few. Not a lot. So if we have more, then I may change because the majority happy with where they are. Just only maybe one or two. Maybe one or two, not really happy. So I'm still debating. I maybe switch that too. But the rest of you, good, right? The rest of you, because I want to go with the majority first. Okay. Okay. Anyone want to check him? Because he been a Lone Ranger, right? Anyone
I didn't even email you. I was going to commit something, neither of them are here.
Nobody would hit you today. Okay.
That's crazy.
All right. Anyone want to check him? He didn't email me. Okay, but he liked to be Lone Ranger. Okay. All right. Give him a hum. Okay. Check home. All right. But if I have more requests, I may shuffle the whole group again. But just one more week. I don't want to mess up the harmony between you guys, right? Okay, C, what would that be? A constant, C. Okay, basically, I have you with this. I have you with this. This is the best thing I can have you. Everything, right? Literally. You just fill in the blank. All of them has to be that. That basically is now the rule. Find antiderivative, put the plus C at the end. Okay. Then, okay, go back to the question. C, constant. X, right? No, not yet. If it is 1, then take derivative, antiderivative will give you 1. No, I mean, hold on, I'm tripping. Right? A constant derivative. Yep, correct. Derivative, this one, give you this. This is antiderivative of this. This is antiderivative of this. But if I have 2, then what would this one should be? 2x, right? C? Cx plus C. Cx. That those two letters C is different, just a constant. Remember, C is just a constant. Could be any number. They don't have to be the same. Okay. Now, x to power n. This one trickier. Earlier, we had x squared. We did the multiple one of them, right? 1/3 x3 plus c. Right, we have that. If I change this to 3, this one will be what? 1/4x4. Okay. Actually, I want to see the pattern. 1/3 x3 plus c. 3, we will have 1/4 x4 plus c. Okay, keep going. Now 5 is 5, huh? 1/6. Based on that, generalize it. X to power n. Now, what do I do over here?
You add 1 to the exponent and you divide it by a number.
Which number is that? Okay, correct. The exponent. You just plus 1. Ready? No. Go ahead.
Do x to the power n plus 1.
X to power n plus 1. Correct. Anything else? 1 over plus 1. These two numbers are the same. Right? Plus 1. Plus 1. Okay. That also apply for negative n too. Okay. That also apply for negative n too. Okay. Basically this. If I change this to -2, n is a natural number. Okay, it could be negative number. Same idea. That would be negative n plus 1. Negative 1. There you go. Negative Okay, these two numbers are always the same, right? And this one, basically 1 over, that is 1 over x cubed. Okay. But there's one number, except one number. Except one number. This is a special case. -1. Then what do I have over here? That will be 0 over here, right? Can you write like that? 1 over 0, x to the power 0. Nope, you cannot write like that. It's not this. In fact, it is. Okay. That is 1 over x, right? That's 1 over x. You take derivative of one. You take derivative of which function give you 1 over x? Natural log. It actually ln of x. And even, okay, for this case, even more strict than that, it have to be absolute value. It turned out to be that. Absolute value. And absolute value of x. Because derivative, but this one give you 1 over x. Derivative, this one give you 1 over x. All right. That is special case. Absolute value. Okay. You should, when you do this problem, try to have the handout from the derivative. You're going to see that, right? Derivative of this is 1 over x. Antiderivative 1 over x is that. Okay. Because you cannot use this one. You cannot use power rule. Cosine would be sine or negative sine? Sine. Because when you take the derivative of sine, it gives you cosine. Okay. I think you know this, right? That would be tangent. Derivative of tangent give you secant square, remember? Okay. That is secant. The last three one, okay, you technically need to memorize up to around here and apply them. Memorize not only. All right, down here. The one below, it's good to know. Okay, it's good to know. That, the one down there, you proved that already. You proved that last time in the exam. That is inverse, right? Those are the inverse function. Okay. Derivative of this, we prove it, give you this. Antiderivative of this, give you that. Okay. That is inverse of cosine. Don't forget the plus c. Inverse of tangent. Inverse tangent. Tangent. Okay. All right. So now you have the table. Try that with this. Try that. Find the antiderivative of those one. Okay. So when you find antiderivative, okay, normally if you have a function, then you want to find derivative, you do this, right? Derivative. Okay, now how do you actually write this one out? How do you actually write it? If you were asked to find derivative, you write it this way, with a prime. If you want to find antiderivative, capital F. Okay. Okay, I have you the first one. There you go. Okay, I have you with the first one. E to power x. E to power x. All right. Now the next one. Technically, it should be plus c. Each one of them plus c, and then plus c. But just put it there. I'm gonna formulate it. These together. Okay. But for now, get a habit of putting plus C, plus C. Okay, you're gonna drop it eventually, two of them. Okay. Okay. Antiderivative. Okay. 3 side of x. 3 side of x. Don't worry about number 3, right? Same like derivative, the coefficient, you just throw it outside. Okay, throw it outside. Side of x. What do you think? Side of x. Side, okay, where's the formula? Side of x. Negative, say, all right. Everybody can see this is 3 cosine x. Not enough. Minus 3 cosine. Minus 3 cosines. Okay. The last one. -2. Right at that is really confused, right? Really confused. I never liked the negative in the exponent. So can I write like this? Right? I can write like that, right? The negative, look at this. That power 1 is 1. Nothing. Right? I can erase that power 1. Right? That's just inverse tension. Yep, oh shit, yep. Antiderivative. All right. Okay, now, normally, each one of them has the plus C, because the plus C is arbitrary, it's unlimited number. So each one of them basically the same, right? Instead of writing plus C, plus C, plus C 3 times like that, regularly, normally, you don't have to write every time. You just find antiderivative. Each one of them, when you're done, put the plus C on the back. Okay. Those 3 C, it basically it's a constant. Okay. Think of this. If you have 1 over here, 2 over here, 1 over here, okay, add them up, you have 5 derivatives, still 0, it still disappear, right? So that constant is more or less like a decoration, right? But we have still to put it there to legalize this problem, right? Okay. All right, how about this? Remember, you are not taking derivative, and unlike derivative, antiderivative is, to be honest, it is much more difficult. Okay, derivative is more streamlined. Antiderivative, you have too many options, and because you have too many options, that's also like a double play. Okay, you cannot use everything in the derivative. In derivative, what rule do we have? In derivative, what rule do we have? How many rules do we have? Let's recall. First one, the basic one. Power rule, right? Power rule. That's basically one formula. You also have power rule here, kind of, but one ugly power rule, right? Right here. Right. Second, you have another 3 rule that is also dictate everything you've been doing for the last month, right? The first one, the next second one, product. Third one, quotient. Last one, chain rule. None of them exist. Those 3, they don't exist here. There's no quotient rule. There's no product rule. There's no chain rule. They have something corresponding to them. Okay, They have something corresponding to them, which you're going to study in the count 2. Okay. Different name. It's called substitution rule. It's called iteration by part. It's called different names, but they corresponding to those rules. For now, forget it. Okay. Forget about the chain rule. Forget about the quotient rule. So in other words, you cannot apply quotient rule here. There's no f prime g and as f g prime. Remember, you are not taking derivative. Then how do you do antiderivative? The only tool at your disposal, no more or less, is this table. So your goal is whatever you see, try to turn it into something one of these. Okay, see what I just did over here? I turned that to something I have in there. That is the only thing you can do. Do that to this. What can I do? What can we do to this? To give you, okay, so now you're going to look at the table. How do I turn it, play around to give you one of the table, one inside the table? Okay. And this is also a technique we did before, in derivative. In derivative, there's also a technique like this. Okay. Think. La, la.
Maybe like set the function to y and multiply by t.
Okay, that's one option. But then you try to take implicit, right? Another one too. There will be no implicit. Good. It's good to point that out. No implicit differentiation. That means no implicit anti-differentiation. There's no such thing like that.
Since the numerator has the same term for all the numbers split to 4 over t minus 2 over t.
Right? They have the same t. Remember this? We've been combining the common denominator. Right? I try to tell you that calculus, we try to go backward most of the time. We split the fraction. Okay, 4 over t. 4 over t. Okay, I'm going to clean that up. Can I write like this? 4 times 1 over t. I have something like 1 over t up there. Right? The ln, right? This t over t. Ah, beautiful. Just negative 2. I have something for a constant for negative 2. In other words, I have formula for each one of this. Then what would be the antiderivative? You tell me. Huh? Think. Okay, finish that. Okay. I can see some smoke from your heads. Right? Right. It has to be like that. It should be burning. It should be cranking a little bit. Okay. You literally reverse everything you've been studying. Okay. You look at it in another direction. Okay. And in count 2, if you go to count 2, if you survive this count 1, I hope you will. And then you go to count 2, you do this like every other week. 1 week you study something in derivative. The following section, you're going to study the antiderivative, the backward version of that one right away. Okay, you have to flip, you have to be adapted to that. It's true. Okay, I have 4 natural log of t, right? Nope. Don't forget this. Okay. Minus 2 t plus, okay, technically I have this 1 over, okay, t, right? And 1 over n plus 1, t to power n plus 1, right? And in this case is 1. So plus 1 will be 2. There. It's never complete without general antiderivative. You are finding a family. Okay, somehow the whole family lost, just not one. Okay, you're finding the whole family, right? There you go. That's a really weird example, but somehow it worked. Right. Next one. Now you're going to find an actually specific one, given that. We're going to come to this later. Why do you have this? Come to this. But for now, both of them are relatively simple, right? Practice that, practice. Okay, so basically you have 4 x to power something minus 3 x to power something, right? You just have to fill in the blank. Fill in the blank. And in this case is 2 and 5, right? 2 and 5. Therefore, I will have, down here will be 3 x 3 1 over x 6. Don't forget, plus c. Okay, simplify a little bit, kind of clean that up. Okay, 1 over 2 x 6 plus c. Okay, so right now you are having this is a family, aka general antiderivative. Okay, general, that is the word. You have plus c, you have general. You have unlimited function. Then you have this. Okay, instead of asking to find the whole family, they want you to identify that c. Okay, I want to find a specific function inside this family that satisfies this. That is this one right here. And this one usually is called initial condition. Okay, in differential equation, it's called initial condition. Initial condition, what does it mean? That means the condition in the beginning, initial condition, right there. If you do this problem in terms of time, t, time, then t equals 0, you plug in t equals 0, that is in the beginning, right? It's called initial condition, right? So t equals 0 or x equals 0, or in the beginning position, right here, right. In the beginning, where am I? Where am I on here? Initial position, right? Initial condition, right there. At the 1, right here. When the clock starts on the race, when the clock starts, 0, I'm exactly right here, aka initial condition. Okay, so this is initial condition. Okay, we use that initial condition to find a specific c. That's it. Instead of a family, unlimited, now we identify exactly one. How? Plug in. So you have f, capital F right here. To find that c, you plug in. When x equals 0, plug in 0 here, here, here. Let that equal 1. So f of 0 equal 4 over 3 times 0 cubed minus 1 over 2, 0, 6 plus c equal 1. There you go. There 1. So that cancel. C equal 1. So for this particular, this specific function, okay, instead of calling it specific, that is the name, particular. antiderivative is plus 1. Okay. Just a few vocabulary, a few new vocabulary, okay? If you have plus C, you call that general. General, because you have too many to call. Then you plug in initial condition, whatever the condition they give you find a specific C, a particular C, you end up with a particular function right here. Right. Now this one is not unlimited. That one is completely only one function. Like look like this. Right. Limited. General. Particular. General. Any question? Any question? So when you're given an initial condition, you know what to do, right? Use that to find C. Okay. There. This is one of very good example to practice you to do the reverse engineer. Okay. Reverse engineer. Why do we learn this? Okay. Usually you have a function. Then you ask you to find second derivative, right? First derivative, second derivative, to take derivative, to do the derivative test. Remember that? Take the derivative twice, then you get second derivative. Now you given second derivative, you trace backward, find the original function. See that? See that? But why? Why do we learn that? You have position. Derivative will give you derivative. That is derivative of position will be velocity. Everybody know that. But do you know that second derivative? Acceleration. Right. Now, later on, just about maybe a couple more examples. Actually, the next one right there. You have this. That's basically this. You give an acceleration. Find the position after a few seconds. Okay, we prepared to do that. Okay, let's go. So, second derivative, it is to find the first derivative. That means you go backward. Okay, you go this to this. You do derivative, right? Derivative. But now you go the other way, you antiderivative. Right? Antiderivative. So antiderivative of this. Both of them are easy to find, right? Antiderivative of that. And then to find the original function, you do it one more time. One more time. 2 times like that. Okay. Try that. Careful with the plus C. Careful with the plus C. Let's see. No. -2. Okay, only when you have 1 over x, or x to the power -1. Specifically that right here.
Yeah.
Then you have the ln. Everything else is this one.
Right.
The 1 over n plus 1. That's -2 right here. Mm-hmm. Only 1 over x, or x to negative 1, then ln. Everything else is different. Okay. That is correct. Now you have that. That is ln. Still have the negative 1, correct? Correct. But how about this c? No. Go to the formula. There's a constant. There's one line for the constant.
Oh.
There, another c. So you another c. So right there, this one. That is cx plus c. Okay. So that is the n, right? And in this case, remember, n could be negative. N could be any number except for number negative 1. Negative 1, then you have to do the natural log. Any other number, you do the 1 over n plus 1. N plus 1, negative 1, x to the power negative 1. Okay, 2 is 2. But e to the power x. Okay, right, e to the power x. Don't forget the e plus c. But I'm gonna use another color for that plus c. Okay. Okay. Next one more time. That is negative 1, the special case. That is 1 over x, right? 1 over x. Because if you use this formula again, you're gonna have 1 over 0, which you don't want. That is special case. You're gonna have natural log. Where is that? Natural log. And the antiderivative, don't forget the absolute value. Okay. This give you this. Don't forget the negative 1. All right. Any question? Okay. Oh, that e to the power x. Okay, that icing on the cake. All right. I like that one. C. We have something for C. Cx and another c. Right, c, a constant. We are this step. Give you another constant. Cx. So in other words, you have 2c. C, that red c, plus, okay, x plus another c, the blue c. This one over here. Okay. Okay, then how do I tell the difference? Because you're not going to have red ink pen and blue ink, right, in the exam. You have two different options. When you have different C's, later on in Cal 2, you're going to have around 4 to 5 C's. So how do you tell around different those C's? Give it a number. C1, C2, there you go. To tell that, oh yeah, that is 2 different C. Okay, or C is a constant. C is just arbitrary. That is literally an alphabet letter. How about plus D? If you want to keep the C, CX plus D. Use an alphabet. Okay, to tell the difference. This C is there. This D is the new one. Okay, or C1, C2, C3. Okay. Okay. So far good? Any question? Any question? Okay. Should I go to position? It's gonna be question. Yes, go ahead.
When you have like multiple C's,
Constant.
you can just like do any letter of the alphabet just to like symbolize the constant.
Yeah. You can do any letter alphabet. Or you can just notate them with a number. C1, C2, C3, C4, or A, B, C, D, E, L, right? Run down the alphabet. Okay. Okay. I'm gonna scroll up a little bit. Okay. One more example. Okay, we can still go with this example. And then have a break. Okay. I want to go into this one, why still hot, with this example. Okay, they are very similar. We're going to do something similar to this, but in a word, okay, with wording. We have second derivative. So that means you are about to be given an acceleration. You will be asked what will be the position after a few seconds. There you go. Same problem. You're about to do something really similar to this, but in this frame. In other words, acceleration, velocity, position. That's it. Okay? So recall position. There you go. This one right here. Velocity, acceleration. Okay. Right? And velocity is just first derivative. Acceleration is the second derivative. Okay. So going backward, you're going to go back to velocity, go back to the position. In other words, you have second derivative. You go back to the first derivative, and you go to the original function. Okay, you just did that above. Okay. Okay, read our problems. A car speed run, not really speed run, 25 meter per second, 24 meter per second, 24 meter per second. How fast is that? Anyone in physics, in engineering, you get a habit of visualize, quantify a number. Like when you hear a number, when you listen to something, don't just think of it as a number. When you say, okay, give me 2 liters, drink 2 liters a day. Everybody should drink at least 2 liters of fluid a day, water a day. Try to visualize that. I'm going around yesterday, I'm speed run. Yesterday I run the red light. Nobody caught me near Costco. Well, not that easy at around 12 p.m. So nobody caught me. Yes, I ran the red light at around 40 miles per hour. Try to visualize that. Okay? Try to visualize that, 40 miles per hour. Okay? Skip the red light thing, but visualize the 40 miles per hour, right? And then in the freeway, when you listen to the news, a car got crashed at 70 miles per hour, or 80 miles or 90 miles per hour. When you hear that, you should assume that person died already, right? That's how you visualize, right? You hear a crash at around 100 miles per hour, a motorcycle, blah, blah, blah. Okay, you don't need to read the full sentence. You know that one person should be, go to Jesus, right? So that is how I visualize. So 24 meters per second. Not really your units, right? That is around 50 miles per hour. Okay, 50 miles per hour. Okay, so when the driver see a kid crossing at around 48.1 meter ahead, keep in mind that 0.1, huh? Okay. The driver floor the brake, yes, yeah, with all his mighty and so, yeah. At the constant deceleration, there, constant deceleration, okay. Floor the brake, see a kid, floor the brake, okay. All right. At deceleration. The distance start counting. Okay, the distance. That means this experiment, this calculation, everything we're about to do, start when he saw the kid. Okay, when he saw the kid. That's mean around here. Okay. Find the velocity at any time t. Find the velocity at any time t. And then find the distance travel before the car stop to stop. Okay. Last question. Did the kid survive? Okay. In other words, where did he stop? Right? Did the kid survive? Okay. Let's try to find out. Okay. Read this problem. Try to put down. Put down what is the given. What do you have? Think of it. Give it a couple seconds. What do you have from this?
The car's velocity.
Car velocity. But it's also, this is a problem about time. So yes, velocity, but think about when it will start. Velocity is 24 meters per second. Okay, now we're going to attach something to the every unit we have. Velocity, yes, we have velocity. Velocity in the beginning or during the crash or at the end. They're all different, right? So that acceleration, deceleration, that would be a rise of t equal 6 meter per second square. Right? Any physics in here? Every engineer in here? Okay, point out my mistake. Yes. Deceleration. That letter deceleration, not acceleration. You are slowing down. That deceleration. Okay. Okay. Now use that. Think about the velocity. Okay, so now you have negative 6. There you go. Start with that. That's what you're going to start with. That's your anchor point. Negative 6 meters per second square. Find the velocity. You have acceleration. Basically, you have this. Find the velocity. What do? Antiderivative one time, right? Part A, find the velocity v sub t is basically antiderivative of the acceleration. Clearly, or both? Yeah. And acceleration is negative 6. Now I'm going to drop the unit, okay, because we don't need the unit here. So negative 6. The velocity will be negative 6 t plus c. Right. There you go. Okay. At any time t, okay, you need to have c. Because this in particular, remember, this is a family. This is a set of many velocity. Okay, in many velocity. In this particular incident right here, okay, in this particular incident right here, you will need to have a particular c corresponding to that. Then how do you identify this c? Anything you haven't used?
48.1 meters ahead.
But yes, we have used that. We're going to use that, but not for velocity, because that is the distance. We have the velocity. The car is traveling at the speed. We haven't used that number right here. Okay. The car is traveling. The car is traveling. The car is traveling. This is the road. Kid here. Kid here. Car over here. Okay, traveling. See the kid, start the brake. This is the moment it start the brake. Right? So what is that? Okay, all of this time, from here to here, he was traveling at the speed 24 meters per second.
I don't get the deceleration. Wouldn't that mean that if it was negative, wouldn't he just instantly go backwards instead of forward?
Oh, acceleration, that means slow down. Backward and forward is the velocity. The direction, you very good point. If you have a negative for acceleration, it tells you it's slow down or speed up, but it's still the same direction. It doesn't tell about the direction. The velocity, if it's negative, then you're going backward. Positive, going forward. Okay. So did I answer your question? Okay. So velocity tells the direction. Acceleration tells fast or slow. Okay. You are going slow down. Okay. All right. So back to this number, 24 meters per second. In this context, when does that happen? When does that happen?
Very beginning, up until he breaks.
Yeah. At the moment he brakes, he was traveling at 24 meters per second. Right? At the moment he brakes is also the moment this problem starts. right? This problem start, right? This incident. So that is the initial condition right there. Initially, at the moment the police or whoever bystander they watching that, he was traveling at 24 meters per second. Okay, somehow the camera or the CCTV caught this incident at that moment before he started. See the kid, V of 0, T of 0. At the beginning. V of 0 equal negative 6 times 0 plus C equal 24. Drop the unit. Okay, drop the unit. We bring back the unit later. C would be 24. Therefore, now you have a complete velocity. Velocity, actually the particular, not just general anymore, velocity of the car in this incident is negative 6t plus 24. There you go. You have that velocity. That's part A. Okay. Next, find the distance traveled before the car come to stop. Find the distance traveled. Distance. Let's start with that distance first. The distance, what do you think? How do you find distance generally? Distance would be, right, position, which is antiderivative of this one more time. Actually, I'm going to write out again. Antiderivative. Later on, you don't need to write all of this, right? You understand the concept. Antiderivative of velocity. Therefore, can you take derivative of that one more time? And this where you can throw in the unit, meter per second, not per second square, right? Per second square would be the acceleration. Okay, what would that be? Antiderivative, one more time. From here, lead to this. That would be, okay, I'm going to use S sub t, I'm going to use the blue one, okay. That would be negative 6 t square over 2, right? N plus 1 over n. How about the 24? 24t. And don't forget the, let's see one more time. And that will be general distance for any case, many cases. Okay. One more time. We need to find a particular distance for this incident over here by finding that c. Okay. But we start running out of option. We start running out of option. Okay, we need to find that c. Okay. Find this. Okay, you need to find that to have the particular distance. I'm going to read the question again. Read the question in part B again. Okay, done. I'm going to scroll up, huh? Okay. First of all, just so you know, we're not going to use this number too. Not in this case, because it's not really plug in anything to get that. We don't plug in, right? It's not the initial distance, right? The car over here, the kid over here, they around 48.1 meter. Okay, so that is not initial. This is not initial distance. So we cannot use this. We cannot use this. There's something else we can use.
Can you set the derivative to 0 and then like use the points to see it where it stops, the car decelerates, comes to a stop?
This work. Correct. I'm going to rephrase the whole sentence. You say let the derivative. But instead of saying derivative, this work. When something stops, last time, the bone, throw up. I asked you, when does it stop? What happened? When does it stop? What happened to its velocity when something stops? The velocity has to be 0, exactly 0, right? Any movement, any object, the moment it stops, velocity 0. When it stops, velocity is 0. Velocity is the derivative. You need to find when it stops. Find when it stops. When, that means t. Right? When it stops, that means the velocity has to be 0. We have velocity right here. Set that equal to 0. So for t. T equal negative 6t equal negative 24. T equal 24 divided by 6 is 4 seconds. Okay, so right here, start 0, t equals 0, 1 second, 2 seconds, 3 seconds, 4 seconds, right? Stop. Then how do we know the distance, total distance? How do we use this number, that t equal 4, to find the total distance? Yes, we plug this to the distance right there. Okay. Negative t squared over 2 plus 24t plus c. Oh, actually. Okay. And that c, now I'm going to give it to you. That c, for all the distance problem, you need the initial condition, same like the velocity. You need initial condition to find the c for initial condition. For a position, initial condition always give you the c equals 0. Okay, that I'm going to skip on the proof. Initial condition of distance ultimately give you c equals 0. You can assume that when you see this problem, c equals 0. Okay, so you're going to have this. 4 squared over 2 plus 24 times 4 plus 0. Okay. That would be, how much is that? Okay, can anybody calculate that? 40? Exactly. 48 would be the, what would be the unit?
Meters per second.
Distance.
Oh, just meters.
Meter. This is the distance the car travel before it stops. You travel 48 meters after 4 seconds. 48 meters. Can you answer the last question? Yes or no? Right. Barely. Right, barely. Yes. Right. The kid would be thanking Jesus, like hold him, right? Oh, the kid survives. Could the kid live? All right. There you go. See how antiderivative apply right away to something you learn, right? You have velocity, you find acceleration. Now you have acceleration. You find exactly how far the car travel. Okay. Take 10, come back, more fun. Bye. Should be chemicals.